vanishing derivative. And then the proposition is saying that two things can happen. Like, first of all, we take the integral now along this curve that we get from taking phi to be just like recomposing the phi to get a different curve. So this one is another curve. And we take the integral along this curve, and then two things can happen. Either we get the same result, or we get minus the same result. And that depends on the sign of this derivative. So it's, because it's non-zero, it's either positive or it's either negative. We get a plus sign here if the derivative is positive, and then we get a minus sign if the derivative is zero. So this minus sign just says, like, essentially, for example, that if you go like with the curve from, like, if that's your original curve that goes in along this direction and you integrate along a one form, then if you turn around like and go in this direction, then you get like minus this the result. So it's like if you change the orientation of the curve, which is like essentially saying that they have a derivative that is smaller than zero, that changes to the orientation that you walk around, then you get minus the same result, and otherwise it's invariant under this reparametrization. So it's the statement that like says that whatever kind of parametrization you choose of the curve, it's essentially the same if the parametrization is like positive. So I don't want to give you the proof, but like it's essentially you do the same kind of trick as what we have done over there, is where you just essentially write down the definition of the left-hand side, then use some theorem that you know from your calculus class, probably something with substitution, and once you do that, you get like a certain expression, and then you calculate this expression in terms of the integral again. So it's a small little nice homework that you can do. Okay. So that was like quite a lot of abstract mathematics. So I would like to give you some idea of where these kind of integrals show up. And one of them is, of course, in physics. So what you can think of is that in physics, what you usually have is that this one form that you look at, that alpha here, is giving you kind of like the force field. So like, for example, you have like a certain gravitation that like pulls this bottle like down. That's why it's falling. So you have like certain a field of force lines that says like how much you go down in a certain direction. And you can think of that as very similar to this example that we had before, where you can think of that as a certain vector field. Or, as what is actually a bit more convenient, is to really think of that as terms of having that really as a one form. So this one form really you can think of that as a certain pulling of like, or a certain gravitation or a certain force field. So in physics, the one form you think of like this alpha as a force, then if you integrate like this force along a curve, that means like you kind of like are like a particle or someone moving in this force field, and you integrate essentially your resistance. So what this is the work that you do. It's the work that you perform if you move along this curve, how much work you have to push like on the particle in order to bring it to the end point. Particle that travels along the curve C. So in this language, this proposition that we just showed just says that it doesn't matter like how fast I'm traveling. Like it doesn't really matter if I'm like super fast at the beginning and then like slow at the end. It really just matters about like the path that I'm traveling along. That's something that you know from physics. It's that like the work done between like going from here, like if I have to lift this bottle and I have to lift it up. It doesn't matter, like the work that I do. It's like doesn't matter if I do it really fast or not. It really just depends on like the endpoints between here and here. And it also doesn't depend on like if I move like this. And that's actually the second theorem that we showed here. Is that for certain kind of forces, it doesn't depend on the path that we go. Like the path C doesn't depend. But like it only depends on the endpoints of the path. So that's like this case where you say in potential energy and gravity, for example, it doesn't matter the work that I do between here and here only depends on the two endpoints, like on the difference in the height. I can like go like this, and that's the same energy as like this that I need to, or like the work that I have to do. So that's like encoded in here. So let me write this down. So force field of the form alpha equals df is called conservative. With F being then the potential or the energy. And then the statement that we showed before is that, that in this case the work done only depends on the potential difference. Of the potential at the endpoints. So the work that I do like depends only on the difference of the potential at the endpoints. So that's like something if you're like physics inspired, and what we do now is like talk about certain conservative forces that usually is like defined just like on some open subset. But now we can make that sense like the same calculus and the same kind of expression that you know from a particle that like maybe for example constrained to move on the sphere or something like that. or has some, like is constrained to move on some really complicated object. And we can already talk about it in the same kind of language by saying like, this kind of F is the potential, and then dF is the one form that is kind of the work. So that makes like all kind of sense, even now for like curved objects. So that's a bit like one of the advantages of these differential one forms is that like certain things that you know from open subsets relatively straightforwardly generalize to curved objects. So like here are like some examples. One of them is like the notion of work and like conservative force fields. Also like some statements from calculus, like the fundamental theorem of calculus, and like in some way invariance or variance under reparameterization. No? So these are like all things that you know from open subsets, and now we know them also for surfaces. And that's one of the advantages of like these differential forms, is that they somehow automatically give us the correct behavior, so that we can translate these statements. Maybe the if you want one exact way to an integral. So let's say we have a curve which is in the open subset of R2, and then we cut out one the origin. So the curve is like going around very complicated, and we have the origin around that. So something like that, for example. And let's say this curve is closed. And it's never hitting the origin. That's the important point. And we can write it. It has two components as C of t. You can write this as x of t and y of t for two functions. And we define a one form alpha on R2 of the origin by saying that alpha equals to 1 over 2 pi minus y dy plus x dy over x squared plus y squared. So that's a particular form. So let's calculate what the integral looks like. So we just go back to the definition. So that's the integral along a to b on, and what we have to do is now we just plug in the curve in this one form, and then we get the following expression. We have to integrate it. So at that point I didn't do much, I just like inserted y of t for the function y, and then we have to evaluate the one form dx on the tangent vector ct of x. Of course, c dot of t just has the components x of t and y of t. And if I pair that now with dx, So we can also write this, maybe if you prefer, as x dot of t in x direction plus y dot of t in y direction. So that's of course the same thing because x was 1, 0 and y was 0, 1. So this is like equivalent. And then we now have dx of that guy. And then we use the definition of dx so that it only eats this part where dx is like written. So that, in particular we get that dx hitting 0 of t just gives us x dot of t. And similarly for y, we get the y component. So if that's the side remark, then we can write the formula now as y of t x dot of t plus x of t y dot of t over x of t squared plus y of t squared. And that's just something that you can calculate for an arbitrary curve. And if you think of that, or think about this for a little bit, you recognize that it's something that you might have seen already in the curves. Namely, it's just the winding number of that curve relative to the 0 point. So it counts, this integral counts how often you wind around this origin in terms of like the x and t. So last time when we discussed the winding number, I told you that there is an expression in terms of like in the relatively ugly looking integral. Here it is. So it's just, once you have a curve, you can calculate the winding number in terms of that integral. So the slightly interesting part of that formula is that this integral a priori is just like an arbitrary real number. But the winding number is always something discrete. So it's like only 1, 2, or 3, like 0. So it depends, like it's very discrete, but this one, you might think if I change x slightly a little bit, then this integral might change also slightly a little bit. But like all contributions cancel out, and then you get just like the same number again. So that's just like as an example that certain expressions that you care about the curve can be really measured in terms of integrals of a given one form along the curve. Okay. So that's all I want to tell you for today about one forms, but I have to torture you a little bit more. Namely, now we talk about two forms. So one forms were things that we're measuring essentially how one vector has a certain property, for example, how much that it points in a certain direction. And like two forms now take like two vectors and give you some kind of number that says how these two forms relate, or that these two vectors relate to each other. For example, it could be the inner product, but it could also be some other property of like the vectors. So like the one forms eat like one vector and give you a number of one vector, and two forms will eat two vectors and give you also a number in a certain linear way. So that's abstractly what like a two form is doing. And like the point why we talk about two forms is because we could integrate one forms along a curve, where we say like, okay, we have the curve and we plug in the tangent vector of that curve, and then integrate over that. So that was the one form. And now we would like to talk about what is the integral of something over a certain surface. So for example, I would like to integrate a certain function over that surface. And that's something that we would like to talk about because during the course that kind of question comes up quite often. And the two, or the things that we can integrate are like these two forms. So we have to talk about them. form, it's one vector, and a 2 form, it's 2 vectors. That's the slogan. So the definition of that is a differential for 2 form on a surface S is for each point of the surface a bilinear map I will tell you in a second what bilinear means, which we write as beta P in that bilinear map. It eats 2 tangent vectors and it gives you a number. And such that it's, if you have 2 vectors and you plug them in, and then you reverse the order of these vectors, you get exactly minus sign. If you have 2 vectors, you plug them in into your beta, and you change the order, you get the minus sign. So it's skew symmetric or antisymmetric. And we will see in a second that this skew symmetricity is essentially what is needed in order to talk about integrals. We call that bilinear means that if you have vectors CV and U, and we pair that with a given vector of W, then we can plug them out to get for all U, V, and W of your Tinten vector plus and you get like the same kind of argument in the second slot as well. That also follows from this antisymmetric. So if you have like the same property in the first, you can just like change the order and you get the same property also in the second slot. And note that because this one is antisymmetric, we have in particular this bilinearity that if you plug in the same vector in both slots, you always get 0. And then you can already guess is that the K form is a multilinear map. So it's satisfies this property, and it eats k vector. So it gives you some number. And that is pairwise skew symmetric. Don't be afraid too much about these ones. They almost never occur for us because we really restrict to 2 dimensions, and it turns out that if S is 2-dimensional, then these ones are always vanishing. So essentially, we don't need to look at these ones. So for us, it's like 1 and 2 forms that are interesting. But I wanted to give you the general definition that you have seen at least once. So the important point here is that we have like a gadget that measures, like eats 2 tangent vectors and gives us a number in the sense that it's linear in each of the vectors. And if you turn around the vectors, you get a minus sign. So that's the important part of a 2 form. And to maybe motivate a little bit of like why we want a minus sign there, we call that like if you have an integration over a 2-dimensional object, so if you have like a double integral, then you might have seen that if you change like coordinates in a double integral, that gives you the determinant of the Jacobian matrix that you might have seen like in your analysis course. That if you have like a double integral, so 2 integrals, and you change to, like some coordinates there, then what you get is the determinant of the Jacobian. So the determinant is giving you some kind of information of 2-dimensional integrals. And let's see how the determinant occurs here. And the way we do that is by just having a look at these kind of 2 vectors. So let's just go back to the definitions. So A, B, C, and D are just some numbers, and V and W are some fixed tangent vectors. So what we do is we just use linearity in each of the arguments. There, we first do it in the first one. Class So that's just using linearity, say for like with respect to the first one. So every time we have a constant, we just plug it out, and the sum of the vectors we also plug out. So now we can do it in the second argument. But what you see here is that what happens is that you have beta of then the 2 times the same tangent vector or scaled ones, and then we use this property that we have like at the bottom that this term vanishes because it's the same tangent vector. And similarly, here, you have also one term where the same tangent vector is plugged in. So these terms vanish. So what we only have like 2 of these terms. And so maybe I'm just plugging these out. So what we have is we get an expression of this form. What you see is these two expressions are the same, except that we are swapped the order of the vectors. And if you swap them, you get a minus sign. So what we get is AD minus BC times this expression. And this expression here, you might recognize as the determinant of this matrix. So what this shows is that this expression of when you calculate it on a certain linear combination, because we get here this minus sign, which comes from this antisymmetry over here, it's like this minus sign. This minus sign gives us like this minus sign over here, which makes us possible that we can connect this expression that we get here with the determinant. If there would be a plus here, then that would be not the determinant. So there's a relationship of these antisymmetric two forms. So two forms are related to a determinant. And the idea behind that is that integrals, or double integrals, also involve the determinant. So that will, next time, we'll discuss about how to integrate two forms over a surface. And what we then will see is that these two connections with the determinant are important. But here you get the first taste of, okay, why we had the minus sign over there to give you some motivation of this antisymmetric property. Okay. And then the final definition for today is a construction that tells you that once you have two one forms, that you can plug them together and combine them to get a two form. So you can think of that already. If you have one form that eats one vector and a different one form that eats also a vector, you combine both of these sketches so that each one eats one tangent vector, and then you just have to think about how to preserve the antisymmetry. So it's called a wedge product. And the idea is to combine two one forms to one two form. So we have alpha 1 and alpha 2 one forms on S, say, then the wedge product, and it's denoted by this funny symbol where we have alpha, wedge, alpha 2, so it's it's a wedge, and that's where the name is coming from, is the true form on S defined by I have to define that. So alpha 1, alpha 2 is a true form. So I have to give you a point, and I have to give you two vectors. And now I have to say what this number is. Naturally what you expect is that we take alpha 1, that one naturally eats a tangent vector at that point, and then we just multiply it by the number that we get when we plug in W into alpha 2. The problem is that this expression is not antisymmetric in V and W. So this, what we call that, like we had this property here, that if you interchange the two vectors, you get minus the answer. But this expression doesn't really necessarily satisfy this. So what we do is we just force this antisymmetry by changing the roles and plugging in the vectors in a different order as well. So this expression here is just to force the antisymmetry. And that you can check as really like really satisfy this property that it's skew-symmetric, and because each of these arguments was already a one form, and so a linear map, we get like that the expression is linear in each of these operations. And the nice thing is that we have certain properties, namely that alpha 1 wedge alpha 2 equals the same thing as alpha 2 wedge alpha 1. So if you just look at the definition, if you interchange not the order of V and W, but let them fixed, but interchange alpha 1 and alpha 2, what you get is the same expression except with the minus sign. So that means that alpha 1 wedge alpha 2 is minus alpha 2 wedge alpha 1. So you have this property, and the wedge product is linear in alpha 1 and alpha 2. So if you consider the wedge product as a linear operation, you see that also from here. Alpha 1 occurs exactly 1, so if you scale alpha 1, then the overall result gets scaled by the same factor. Okay, so I'm running out of time. But I still want to give you one example so that you see that in action, and maybe don't end the lecture with just like nonsense. So let's consider on R3, we can define alpha by A1 dx plus A2 dy plus A3 dc. So it's a little bit more general because it's like on R3, but and now we can calculate what alpha wedge beta is. And because it's linear and you can just like collect all these terms, what you get is that it's A1 B2 minus A2 B1 dx wedge dy plus A2 B3 dy wedge DC plus A free B1 minus B free A1, and then here we have DC times dx. So what you get is like let's look at the first factor. We have dx and dy. That gives you A1, B2, it's this term. And then we have the same term with dy dx, which is A2, B1, but we get a minus sign because they were 0. There's no terms where they both occur at the same time because that's antisymmetric. So what you see is that it's A1, B2, A2, B1, and then these other coefficients. So the coefficients are the same thing as the cross product if you think of these as vectors. So the coefficients of this wedge product is related to this cross product that you know. If you think of a vector as like as a one form in these two different ways, then the wedge product gives you essentially the cross product or the coefficients of the cross product. So that's maybe already one motivation why you might be interested in this kind of wedge product, because it generalizes like cross products that you know from early on from kindergarten to something now that is like making sense on the surface. And that's a bit like the motivation why we need this wedge product to talk on the surface. I'm sorry that I took a little bit longer. So enjoy the rest of the evening, and we see each other. We see each other then next week. Yes, you could define a map like a one form on the surface. That's possible.
Yeah, I just received the notification that this document, maybe I just erase document and the invoices to some place and finish the last one.
Sorry, that was a bit too fast.
Yeah, I just got a notification that I printed this document and yeah, maybe I should deliver this document and the invoices to some partner. Yes, I can complete the last step of the.
Okay, good. Okay, good.
Yes.
So yeah, I accepted it, but it's good that you got a notification. So you have to hang it in somewhere.
Yes.
Okay, do you need to sign something?
No.
Okay.
And yes. Pass here. So V is the convex linear space, and I is the linear map of continuous open space building, and P is a seminorm.
Yes.
And so why there's less? But because we can't even compare which is big and which is smaller. But there's like P is a seminorm and eat the IF to a number.
Yes.
But here, the right hand side, the I of someone is B. So it's a number, the right hand side is a vector.
So you're asking why?
Yes. So
why they are not equal, or?
No. So I ask, what does this mean?
That's a good question.
Yeah, and P is a seminum, so this left hand maybe even a convex number.
It's the same problem here, huh?
Yes.
It doesn't make much sense, right?
Yeah.
What is it? Like it's probably something with like integration, no?
Yeah, and as it's inequality, we need both sides to be a real number. But it's a vector. It's a complex number.
Yeah, so what I think is what this one is like the integration, right? Like really, really strangely written. But like my guess is that you have I. You have J. Once you have like an integration of some integration in this sense, you automatically get like the same observation in terms of this, and then it's linear, like it's compatible in terms of sharing with but yeah, like it's really artificial.
Yes, and I just kind of like handphone that asked whether he received this notification, and he received that. No, I don't get. I didn't receive this. Yes, and he didn't need to print some materials, and I don't know why.
And you had to print it? Okay.
Yeah, I just and maybe he missed missed some information. I don't know.
Yeah. Can you maybe ask, like, when you bring it somewhere, like, do you hand it in to the person, or do you just like in a press box?
Yeah, I'll ask tomorrow to the secretary.
Yeah. Also, like, where do you bring it? Like,
yeah, I just printed this.
Yeah, and do you have to hand it in somewhere?
Yes. Yeah. Maybe.
Yeah. So if you have to hand it in somewhere, then please also ask. Like, he also needs to hand it in, or just didn't got the notification.
Okay.
I never had to hand it in, but might be that because you're undergraduate student and there are certain rules for that, or because you're a physicist, you get different rules, then I don't know. You guys have some questions?
I don't get when you write this because
Maybe I should have written it like that. You should think of it like just like just to make it simple. So you should really think of like this x being that x. If you change the point, you get like a different result. But like this y is like saying that we get the one result. So what we see is like ex x y is some integral equals to x dy. In that case, this one is just a number, and this one is a number. So what we get in total is a number, and that's exactly this one. And like this part here, it's like you can really think of that like when I'm writing it like this. It's like this one is a function. That's the coefficient. So that's a function on the open subset. And this one is a one-phase function. So that was like this coefficient function that I defined in the first part of the lecture. So that's really saying that this one form is a function, and the function is just f(x). And dy is the one